Okay, so today we're talking about perpendicular bisectors, and we're going to start with the information that they want you to know coming into this lesson. This is information you don't necessarily already know, so I'm going to give you the background. What I want to talk about is what is a perpendicular bisector, just the definition of a perpendicular bisector. So the things that you want to remember is that perpendicular means that the lines intersect to form right angles, and that a bisector cuts something into two congruent parts, and that's what we're going to focus on. So if we know that line L is the perpendicular bisector of segment AB, then we know a couple of things, and we're going to write those down. We know that AM, segment AM, is congruent to segment MB. And anytime you're talking about the segment itself, you want to draw the little line above the AM and the MB, that the two segments are congruent. Congruent means that if we put one on top of the other one, they would match up exactly. We also know that AM is equal to MB. And you'll notice on this one I switched two things. I took away the bar over it, and I changed it from congruent to equal. When we're talking about equal, we have to be talking about the value of something. Only numbers can be equal to something. Numbers can only be equal to other numbers. And so when we say AM is equal to MB, we're talking about the value, so we're talking about the length of the line segment. When you are justifying something on your homework today, when you're explaining your reasoning, it's okay with me if you choose which one of these you want to use. You can either say that AM is congruent to MB, or you could say that AM is equal to MB. The other thing we know, and I'm going to go ahead and number these two angles, is that angle 1 and angle 2 are right angles. And we know that they're right angles because line L is perpendicular to segment AB. There are times that we need to be really careful with the way that we phrase things, and I'm going to point that out, so listen carefully to when I tell you how to write things. If you would prefer to write this out in words instead of use the symbol for perpendicular, that's fine. You can either use the symbol or you can write it out in words. It's up to you. But these are the things we know about perpendicular bisectors. This is what we know just from the definition itself. So that's kind of what you're supposed to come to 6.2 already knowing. What we're going to look at is we're going to look at a theorem and its converse. So the theorem that we're going to talk about first is called the perpendicular bisector theorem. And it says, if a point lies on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So first I want you to start by writing that down and then highlight any word that you are unfamiliar with. Okay, so which of these words is a word that you're not real familiar with? Equidistant. Equidistant is a word that you don't use much, right? Yes. So you do know about equilateral triangles, right? An equilateral triangle is where all of the sides are equal. Lateral means side, so equilateral means equal sides. Equidistant is going to mean equal distance. So I want you to come out to the side and jot that down. Equidistant means equal in distance. Equidistant, equal in distance. And we're going to come back to this image in just a minute. I want you to grab the little half sheet of paper I gave you. It looks like this. We're going to start with example 1. Okay, I'll get you one. The first thing I want you to do is label that point where they intersect, M. Label that point M. And I want you to measure AM and MB and see what you find. So grab your ruler, measure AM, and then measure MB.
Would you prefer us to use centimeters? I suppose.
Centimeters is going to be easier.
I threw mine at Lauren because I didn't know
Okay, so what is the length of AM? What did you guys get?
4 centimeters.
4 centimeters. And what's the length of MB?
Not 4. 4.1.
So 4 centimeters. Okay, so those two things are the same. Do you remember the way that we mark a shape to show that two pieces of it are the same length? We use the little lines. So we're going to mark that AM is congruent to MB. Is our line perpendicular to our segment? Yes. So is it the perpendicular bisector? Yes. And that's part of the explanation you're going to be doing on the homework. You're going to say things like, because AM is congruent to MB and the two things are perpendicular, we know that this is that L, let's make this L, that L is the perpendicular bisector of segment AB. So the theorem that you just wrote down said, if a point lies on the perpendicular bisector, so you're going to take a pen and you're going to put a point on the perpendicular bisector. I'm going to put mine right here. I'm going to label it Q. It said, if a point lies on the perpendicular bisector, like this one does, then that point is equidistant from the end points of the segment. So that means Q is equidistant to A and to B. So grab your ruler and measure how far is it from A to Q.
Does it have to be Q?
And then from Q back to B. Now, did we all put our points in the same spot?
No.
No. So are all of you going to get the same?
No.
No. But is the length of AQ for you the same as the length of QB?
Well, mine is literally also 5. No, mine is 2. That's actually so scary.
So for mine it was 6. So AQ is equal to QB. That's what this theorem says. So the definition of a perpendicular bisector tells us what the perpendicular bisector is. It's perpendicular to the segment and it bisects it into two congruent parts. What the theorem tells us is if a point is on that perpendicular bisector, then it's equidistant from the two endpoints. All right, so let's look at what a homework problem might look like. Go ahead and write this down and draw the picture. It says find the measure of RS and explain your reasoning. Okay, so when I ask you to do something like this, find the measure of RS and explain your reasoning. If this was a question on a test and say it was worth 5 points, find the measure of RS would be worth 1 of those points. Being able to explain your reasoning would be worth 4. The most important thing that we're doing here is learning how to explain our reasoning. You should be able to look at this based on what we've just said and tell me the length of RS. Right? That part's not the hard part. The hard part is being able to say, do you really have enough information to say that's true, or do you just think it looks like the other one? And so that's what we're working on.
Except because the lines, they're like the same. there aren't.
Because what it's asking us to use is use the properties that we've learned, the geometric properties. I had you measure so you could get an idea of what's happening, but when you're trying to prove something here, you want to use the properties and the definitions that you've learned. So, what do you think the length of RS is?
6.8.
6.8. Well, that would be true if S was where?
On the perpendicular bisector.
On the perpendicular bisector.
It is.
So what we need to do is say how we know it's on the perpendicular bisector. So how do we know SQ is on the perpendicular bisector? What's one thing we know?
Because R and Q, or RQ is equal to QP.
So that's the first thing we're going to say. We're going to say RQ is equal to QP. That tells us that it's bisecting it. So that's the first thing we know bisector does. What's the second thing?
Angles are right angles.
The angles are right angles. So those two things are perpendicular. So I'm going to write it like this. SQ, which is a line, so it gets arrows over it, is perpendicular to RP, the segment. Those are the two things I know that tell me that SQ is the perpendicular bisector. So once I've written those two things, I'm going to say, I know those two things, so I know that SQ is the perpendicular bisector of RP.
So we're going to write down all of this?
Yes, so we're writing out all of this. So we've said these three things. Now because of that, we know that the distance from S to P has to be equidistant from the point from S to R. So here's another abbreviation. These three dots in a triangle mean therefore. So it means I know all of these things, therefore I know that this other thing is true. So we're going to state these, and then we're going to say, therefore, SR is equal to SP, because S is on the perpendicular bisector, so those two things have to be equidistant. And we know that SP is 6.8, so we know SR is equal to 6.8. So these first four steps are the explain your reasoning part. That's our 4 points that we get. And then we get 1 point for this final part of us saying, okay, that means that it is equal to 6.8. Okay. It's going to feel a little bit tedious, but learning how to really defend your argument is huge. Where have you talked about defending your argument before? Debate. Where else?
Drama.
History. English. Anytime you're making a claim and saying, I think this is true, then you're having to back it up with that evidence. And that's what this stuff is right here. This is your evidence of how you know that that's the case. Okay, so that's how we use the perpendicular bisector theorem. Now remember I told you we were also going to talk about converses. And the converse is when you switch the if and the then. So for this one, it said if a point lies on the perpendicular bisector, then it's equidistant from the endpoints. What we're going to do is flip those and say, if a point is equidistant, then it must lie on the perpendicular bisector. And I just realized that we forgot to finish the drawing for this after we did it on your paper. So somewhere on this perpendicular bisector, go ahead and put your point Q. You did it on the little half sheet, but I don't know if you did it in your spiral. And say that AQ is equal to QB. So if Q is on the perpendicular bisector, then AQ is equal to QB. Okay. I'm going to scroll up and have you write the converse down. Whoop. Here's the converse and its image. So take a minute to write this down and draw the picture. Okay, I want you to come back to the little half sheet I gave you, and we're going to talk about the second example. You'll notice on this one I didn't connect anything. I just put point P somewhere above segment AB. What I want you to do for this one is I want you to find the distance from P to A and from P to B. So just use your ruler and measure how long is AP and how long is PB.
6.1. Okay, we're gonna go with 6. It's 6.1.
Actually,
6.1 is.
It's 6.1.
Okay, so if this is 6.1 and
Okay,
this
so
is 6.1,
The other one's 6.
then is P on the perpendicular bisector?
Yes.
If those two distances are the same, then we know that P is on the perpendicular bisector. That's what the converse, this is illustrating the converse of the perpendicular bisector theorem. So we should be able to draw a line that's perpendicular to AB that goes through point P and bisects AB. So you should be able, if you draw a line that's perpendicular that goes through point P, you should find that AM and MB are the same length. So if you measure AM, it should, if you drew it perpendicular, and it can be hard to eyeball a perpendicular line, but it should be that AM is congruent to MB, where AM is equal to MB. So let's talk about the way we write these things. Come on.
It's just like working backwards instead of
Mm-hmm.
So it's like the same, right?
It's the same thing. It's just like
The other way.
the same. Like instead of trying to figure out how big the
The same
line is, you're trying to figure out if it's the same thing.
Yes. One is saying we know that this is the perpendicular bisector, so we know this other stuff. The converse is saying we know this other stuff. That tells us that this is the perpendicular bisector. So they're just
That's what I said.
converses of each other. I was just making sure we said the same thing. Okay, so when we say AB with a line over it like this, that means we're talking about the segment AB. This is something I would write down. When we're talking about it as a segment, we're talking about its shape. So the shape of AB, segment AB. Shapes can be congruent. So you can say segment AB is congruent to another segment. So we use the segment one when we're talking about anything being congruent.
Is it just congruent? Is that all we're going to use it for?
We're using it anytime we're talking about the segment itself. So we also used it when we said AB was perpendicular to something. We were talking about the segment as a shape. When you say AB and you don't put the line above it, that's when you're talking about the value or the length of AB. So when we say AB, it's some kind of a number, like 6.8. And that's when we would use that things were equal, because numbers can be equal to each other. Shapes are congruent. Numbers are equal to each other. Shapes are congruent. It takes a little bit of practice to know when to use which one. In the beginning, you're going to have to stop and think every time you write it down. Does this need the segment over it, or does it not? Eventually, if you do it enough, it becomes second nature. But to begin with, you'll need to think about it each time. Okay, so let's come back to your spiral, where we were writing the converse. And this is where we said, if I know that C is the same distance to A as it is to B, then if I draw a line that's perpendicular to that segment, that it's going to be the perpendicular bisector. And I'll show you how we would use this in an example. So here's our next example. Go ahead and write the question and draw the picture. Okay, so this example says find the measure of EG. So we're looking for how far it is from here to here. Does it look like HF is the perpendicular bisector?
Yeah.
Yeah, so if it is, then we know that EF is the same as FG. So in order for us to use that, we have to prove that FH is the perpendicular bisector. So that's what our statements that we're writing here are trying to prove. So the first thing we know is, do you see that they're perpendicular? Yes, so that's the first thing I'm going to write down because it's the most obvious, that EG is perpendicular to FH. Now I didn't put anything above these because I wanted to talk about why we're going to write what we write. If I'm saying that EG is perpendicular to something, I'm not talking about the length of EG. I'm talking about the segment. The segment EG is perpendicular to the line FH. So since I'm talking about EG as a segment, I'm going to write segment above it. And since I'm talking about FH as a line, it gets a line including the arrows above it. So I know that those two things are perpendicular. What else do I know that helps me know that that's the perpendicular bisector?
GH and EH are equal.
Yes. So we know that EH and GH are both 24. So I know that EH is equal to GH. Because I said equal, you know I'm talking about how long they are, their length. So if I'm talking about their length, I don't need to put the little segment sign above it. EH is equal to GH. On the homework, if you wanted to write EH is congruent to GH, that would be perfectly fine. Either one of those makes our point, which is that H is equidistant from E and G. So we're going to say, since H is equidistant to E and G, HF is the perpendicular bisector of segment EG. I will tell you, when I write these, my wording is not always the very same. If you were to go back and look at the notes I did in each class, sometimes the phrasing of these is altered a little bit. The important thing is that you're telling me what you know and that you're saying all of the important things. Also, if I wanted to say that EH was equal to GH before I said that the lines were perpendicular, that would also be okay. The order that I say those first two things is not important. But essentially, I've said these two things which tell you that it's on the perpendicular bisector. Because it's on the perpendicular bisector, we're going to say therefore now. Now that we know that's the perpendicular bisector, we know that EF is equal to FG. And you know that FG has a length of 9.5, so EF has a length of 9.5. You see how this kind of looks like substitution? I know that FG is 9.5, so I just kind of put that 9.5 in place of it. But then for this one, they asked me EG. Well, that's that whole distance, and each one of them is 9.5. So EG is 9.5 plus another 9.5. So EG has a length of 19. When you are working the homework problems, don't close your notes and hide them away. Have them sitting next to you until you know kind of what the rhythm of the explanations should look like. Okay? As math gets more involved, the way that you explain your reasoning can vary from problem to problem. Because what we're talking about is very small and one simple little skill, most of our explanations are going to look the same. Did you have a question? Okay, so I'm going to scroll up and let you write down these formulas. If you've already written them down off the board, then you don't need to write them down again. But if you don't have these formulas written down, then you can do that now. Did you have a question about this problem?
Yeah.
Okay. What was it about this one?
So what are the necessities for the reasoning?
So it depends on what we know. So we need to be able to say, like, if we're going to use the perpendicular bisector theorem, the first one, we needed, I'm going to zoom out and scroll down. So for this one, in order to show that SQ was the perpendicular bisector, we could use that these two, QP and QR, were the same. So it bisected it and that it was perpendicular. Our other option, if we don't know that, is to show that they're perpendicular and that these two lengths are the same. So one of them is using the original theorem and the other one is using the converse. And what you have to do on the homework is look at what you're given and figure out which of the two you need to use. Okay. Take a minute to write down these helpful formulas, and then we'll talk about this next example. Okay, remember in these formulas that when you see the x's and y's, they're talking about ordered pairs. And also when you're finding distance, when you use the distance formula is used to find length. So write that down. That's used to find length. You would do that if you wanted to show there was a segment on a graph and you wanted to show that this segment and this other segment were equal in length, you would use that formula. Okay. Midpoint formula finds the midpoint of a segment. So do you see how they're adding the x's and dividing by 2 and adding the y's and dividing by 2? The midpoint formula is essentially finding the average of the x's and the average of the y's. That's what the midpoint formula does. When you're looking for the middle, you're looking for the average of the two numbers. And then we have point slope formula like we talked about in the warm-up. And then a reminder that perpendicular lines have opposite reciprocal slopes. So if one of them is 2/3, the one that's perpendicular to that would be negative 3/2. Okay. All right, so this example asks you to write an equation. So that's our first thing. That's what we're trying to do, is write an equation for the perpendicular bisector of a segment with these two endpoints. For problems like this, you do not have to draw a graph, and sometimes it's not reasonable to draw a graph because the numbers are too big or the numbers are fractions or decimals that make it difficult to graph. But because these are relatively nice and easy and I want you to see what's happening, we're going to graph it. I'm going to pause for a second and let you write that down. Okay, so what I want to do, just so we have a visual image for this one, is we're going to go ahead and graph point P and point Q. So P is -2, 3, and Q is 4, 1. So there's our line segment. It's not a great line segment. I'll try that again. That's so we want the equation for the line that's a perpendicular bisector of that. So what point on that segment does our perpendicular bisector need to go through? If it bisects it, what point does it need to go through? What is that middle point called?
The
midpoint.
The midpoint.
So we need to first find the midpoint because we know that our new segment has to go through the midpoint. So remember I said you're averaging the x's and averaging the y's when you find the midpoint. So to average the x's, we're going to add -2 plus 4 and divide by 2. To average the y's, we're going to add 3 plus 1 and divide by 2. Be sure you do the numerator first. So -2 plus 4 is 2, divided by 2 is 1. 3 plus 1 is 4, divided by 2 is 2. So our midpoint is at the point 1, 2. So I'm going to go over here to my graph and plot that. Does that look correct for the midpoint? Okay.
Yeah.
So I'm going to label that M. M is the midpoint. The other thing I know about my perpendicular bisector is that it needs to be perpendicular to this segment. And the thing we know about perpendicular lines is that their slopes are opposite and reciprocals. So we need to find the original slope first. And once we know the original slope, then we can find the new slope. If you have a graph, you can find slope. If you have the graph, you can find slope by doing rise over run. If you just have the ordered pairs, you can use the slope formula. So I'm going to go ahead and use the slope formula for this one. y2 minus y1 over x2 minus x1. We're going to subtract our y's. 1 minus 3 over 4 minus -2. So 1 minus 2 is -2. 4 plus 2 is 6. So our original line had a slope of -1/3. Our new line has to be perpendicular to that. So we're going to take that slope, we're going to find the reciprocal, so we're going to flip it over, and we're going to change it to the opposite. So our new slope, +3. If you want to write 3 over 1, you can. You don't need it. Once we have the slope and the ordered pair, we can use point slope to figure it out. So we're going to use our point slope formula. Y minus y1 equals m times x minus x1. Plug in your midpoint for your ordered pair and our new slope for m. And then we're just going to simplify and change it into a slope-intercept form. So y minus, our y for the point was 2, so y minus 2. Our new slope is 3, x minus 1. That's our equation, but we want to change it into slope-intercept form. So we're going to distribute the 3. So 3x minus 3. And then we're going to add 2 to both sides.
It's -1.
So y equals 3x minus 1. Just because we can, I want to go ahead and graph that line on our graph that we had up here to see if it fits. See if that makes sense. So what's our y-intercept for the line we just wrote? -1. And the slope was 3, so rise 3, run 1, rise 3, run 1. Is that perpendicular?
Yes.
And it goes through the point that we wanted it to. So that's what we were doing. We were coming up with the equation of that line right there. So that's what you're doing on this lesson. You're using the perpendicular bisector theorem and its converse to show that something is a perpendicular bisector and use that information to find certain lengths. And then you're also writing the equation for perpendicular bisectors given certain information.